Okay. So yes, playing with a ball, motion, playing with motion. Yes, motion has its way in everything. It has freedom to move, but motion has its restrictions, and today we are going to talk about how motion gets restricted. What is the freedom that an object has while performing motion? Now, imagine yourself at an amusement park playing, and suddenly you see a large you suddenly see several multitude of rides, the Ferris wheel, the roller coaster, and you try to determine how many ways the roller coaster's coach can move, right? If you try to define or give a numeric value to how many ways this roller coaster can move, then we are talking about degree of freedom. Now, degree of freedom is formally defined as the number of independent ways a body, a particle, or an object can show motion. Now, this has real world applications as well. Engineers at aerodynamics, designing aeroplanes, use this concept to make the movement of an aeroplane more swift and smooth. Robotics has its applications. Suppose a robot needs to pick up an item. What movements does it need to make? It makes sure that the robot doesn't make any useless movements which are not required, and therefore a predefined knowledge of the number of ways the robot can move is necessary, and a numeric value is given to it, and it's represented by degree of freedom. Now, I will be referring to degree of freedom as DOF in this video for ease in not spelling out pronouncing every time degree of freedom. It's a long name, so I will say DOF. Now, degree of freedom. To understand degree of freedom, we first need to understand motion. Now, motion can be classified into three types. First is translational, rotational, vibrational. Okay, let's write something on the board. Motion can be classified into three main types: translational, then we have rotational, and third and last we have vibrational, broadly classified into three types. Now, translational motion, what is it? It is rectilinear fashion motion, straight line motion. Nothing to exaggerate on this. Then we have rotational motion, turning about an axis. Okay, rotating. Its position is not changing, but it's moving. How is it moving? It's changing its orientation, and that's rotational motion for you. Now, vibrational motion, moving about a mean position. Now, this happens only in stable equilibrium cases where this body, suppose I move it, it's in rest state, and now I give motion to it. I apply a force and it moves like this. But what happens is, this is in stable equilibrium when it was at rest. So it tries to get back to that position of rest, and in doing so, it applies a force here and it moves. But it has acquired a velocity and now it has inertia. So due to inertia of motion, it moves to the rest position, but due to this inertia, it moves the same distance on this side before coming to rest, and again the restoring force is applied from this side, and this restoring force drives it back to rest position, and again due to inertia of velocity Now it is moving about inertia of motion, it moves this side. Now it is vibrating, it is moving about this mean position, and this is for vibrational motion for you. Now these three types of motion help us define degree of freedom in these three types: translational DOF, rotational DOF, and vibrational DOF. We are going to study these two cases in detail, and we will not study vibrational DOF because we are going to study about microscopic molecules in gaseous state, and they only show vibrational motion at very high temperatures, extremely high temperatures, and therefore we are not going to take into account vibrational DOFs because we are dealing with gases at normal temperature pressure and not very high temperatures. So vibrational DOF is omitted or neglected. Okay, now talking about translation can take place in x-axis, y-axis, and z-axis. And note one thing: this degree of freedom is not only defined for microscopic but macroscopic objects as well, as introduced in the starting of this lecture. Okay, the applications in the real world, in macroscopic world, and now we are going to talk about the microscopic world, or the world of gases, real gases, not real gases, ideal gases. Okay, so let's talk about a molecule like helium. Helium has only one atom in its molecular state. So let me take a space. Let me define my axes. This is the origin, and I have the x-axis, the y-axis, and the z-axis. These three are my chosen axes along these directions. Now this is my reference point, and the naming is pretty trivial. You don't need to give emphasis on what we name our axes. X-axis is the horizontal axis. You can keep it the vertical also. The naming is pretty trivial, and the orientation as well. It's only for our ease in understanding that we have placed that x-axis, y-axis, and z-axis in these alignments. You can choose any other direction and you can name them anything you want: A, B, C, K, L, M, and anything that your imagination suits. But according to what has been taught to us all over these years and obeying what has been done for past years, we take X, Y, and Z as our three axes in space. The orientation is also like this: X, Y, and Z. If you take any other orientation, or even this orientation and any other axis name, or even this axis name, you need to define them clearly in physics. While talking about space, you can define the axis like this, you can define anything, but you need to clearly state what you are defining, right? You need to show your reference point to everyone who will be seeing you afterwards. Suppose you wrote a lecture paper and you wrote all these, you defined the axes as A, B, C, but you never stated that you are taking the horizontal axis as A axis, the vertical axis as B axis, and the axis towards you, that is into the plane or out from the plane, as C axis. Then it will create a bit of confusion for the readers, and observers might face problem in understanding you after reading your work, right? So coming back to the topic, we have a helium atom here. Now helium atom can either move in the x-axis, it can move in y-axis, it can move in z-axis. Okay, it can move above in y-axis, it can move left or right, up or down. Okay, up or down, this is the whole is y-axis. We are not taking positive or negative y. We are considering this whole as y-axis, and it can move up or down from the origin. It can move left or right, that is move along the x-axis, and about the z-axis, that is into the plane or out of the plane. For example, if I take this balloon, now this balloon, let's imagine this as the helium atom. Okay, it can move up, it can move down. So that's one motion for you. Another 1D motion it can show. It can move towards you or away from you. That's another 1D motion. And it can move left or right. That's another 1D motion. So it can show 3 1D motions. And if you ask me that if it moves in an arbitrary direction in space, then what do you do? Actually, every motion can be broken down into 1D motions. You learned that in projectile. A 2D motion like this can be broken into 2 1D motions. And that's the most fundamental thing. Every motion can be broken down into 1D motions. And therefore, we are only going to talk about motions in x, y and z axis because they are the most fundamental. If they are showing motion in x axis, then it has 1 DOF, translational DOF. If it shows motion in y axis also, then it has 2 DOF, and z axis also, then it has 3 DOF. So, translational DOF for helium atom is equals to 3. Now, talking about rotational DOFs for helium atom. What will be the rotational DOF? If I rotate this helium atom, let me take my balloon back. Okay, so if I have this balloon, I have the z-axis towards you. If I rotate it about the z-axis, are there any perceivable changes? No, right? Okay, let's rotate it about x-axis. X-axis passing like this. Are there any perceivable rotations? It's all spherical from all sides. So there are no perceivable rotations. Now let's rotate it about y-axis. I don't think that there are any perceivable rotations. Therefore, all the perceivable rotations are 0. And also, when we talk about molecules, molecules are very small. Now, to turn something that is very small and its axis of rotation is passing through the center, that is the nucleus, and its radius is very small. Helium atom has a very small radius, and therefore, to turn it against that small radius to produce a torque, the radius is very small, but the torque is reasonably okay, but force needed will be very large to turn it about that axis. Since radius is very small, force needs to be large to turn it. Okay, now let's take the oxygen atom for an example. Oxygen atom is diatomic. It has 2 atoms. Oxygen molecule. Oxygen molecule has 2 atoms. It is diatomic, and we are turning it about the x, the y, and the z axis. But before that, translational DOF is again definitely 3. You can move out all the 3 axes. Translational DOF equals 3. But the major concern here is rotational DOF. How many ways can it rotate? We are not sure of that. Let's experiment with it. Okay, x, y, z. So if we turn it about the z axis, okay, imagine this is the oxygen atom and you are turning it about the z axis. Can you see any perceivable rotations? The z-axis is towards the screen. The x-axis is left or right. The y-axis is above or below. So into the screen, if I rotate it about the z-axis that is passing through the center, you cannot see any perceivable rotations. Therefore, about z-axis it cannot show rotation. Let's take x-axis. X-axis, it's passing like this. Okay, this is the x-axis. It's passing right through its center and horizontally. If you see it in your screen, it will be horizontal, right? Now, if I turn it about this, this is a perceivable rotation. Oxygen atom shows a perceivable rotation, so one we have found. Okay, let's take the y-axis. We have this. Now y-axis is like this. It's vertical to the screen. If I rotate it, it's spinning in the plane xz plane. Okay, it's moving like this. So this is also a perceivable rotation. Only in case of z-axis, about z-axis it doesn't show any perceivable rotation. So I have my rotational DOF as 2 in the case of oxygen. So diatomic molecules are always linear, definitely, and they show 3 translational DOF and 2 rotational DOF. So total DOF or degree of freedom is 3 plus 2, which is 5. Now in case of, let's say, CO2. CO2 is a triatomic linear molecule. Now, one thing to note here is I'm representing atoms in form of spheres. Now, don't get too familiar with this concept, right? This is definitely a good representation of the atom, but for understanding purposes, but actually the atom is not a sphere. Okay, so atoms are not like solid spheres. They are much more expanded, like they have an electron cloud around them and a positively charged nucleus. They have atom is pretty accurate, but it's not the most perfectly correct representation of an atom. We actually don't know how to represent an atom. We are just trying different models, and we are trying to get to the most accurate model our human brain can perceive, and that is what we try here too. I am trying to explain you through a model which you can understand here, so that degree of freedom can be understood with ease. So don't get too attached with this concept of representing atoms, because this is not the most accurate. This is you are using this or exploiting this model so that you can understand degree of freedom, but you don't need to get too much attached to this concept, right? So let's take triatomic molecule CO2. CO2 is again linear. Okay, I have 3 atoms here. They are linear. I'm keeping them about the z-axis again. Okay, now here translational DOF, undoubtedly translational DOF is equals to 3. Now talking about rotational DOF. What about rotational DOF? Again, it is the same linear structure like the diatomic molecule, the oxygen. I have the same whiteboard marker as my representation, z-axis. No perceivable rotations. X-axis passing through here. Perceivable rotation. Okay, this is a perceivable rotation. Now about y-axis, this is again a perceivable rotation. So it again has rotational DOF of 2, and therefore total DOF is 3 plus 2, which is 5. Now in any polyatomic molecule, that is more than 3 molecules, or let me say triatomic non-linear molecule, what will be the case? Triatomic non-linear or any other polyatomic molecule that is having 4 atoms, 5 atoms, 6 atoms and so on. Okay? What happens in those cases? You can try it yourself before seeing my explanation. Let's take H2O. Okay, this is H2O. It can again show translational DOF of 3. Rotational DOF is my question. Now it's something like this. Okay, something like this. I have 2 marker pens to represent this. Okay, you can see this. Now I have the x-axis passing through here. I can rotate it like this about the x-axis. It's a perceivable rotation. Now I can rotate it about the y-axis. I can rotate it about the z-axis, like this. So all these rotations are possible. It's showing rotation in all these 3 cases, and therefore rotational DOF is also 3. So total DOF is 3 plus 3, which is 6. This is what happens in triatomic non-linear molecules, and any other polyatomic molecule will not be linear. Any molecule having 4 atoms cannot be linear. You should have learned that in chemical bonding. Now, let's tabulate what we have just learned. Monoatomic DOF is equals to 3. Diatomic DOF is equals to 5. Triatomic linear DOF is equals to 5, and triatomic non-linear or polyatomic will have DOF equal to 6. Right? This is the table. Now, we have an interesting theorem relating energy, internal energy, to degree of freedom, and it's called law of equipartition of energy. So it says the total energy present in a system, okay, a system of molecules, a gas consisting of a gas, a closed system, definitely, which is in thermal equilibrium, has its energy per molecule, per degree of freedom as a constant at a particular temperature. And this is what law of equipartition is. Let me state that again. In a closed system at thermal equilibrium, the total energy per molecule, per degree of freedom is a constant and is directly proportional to the temperature at which it is observed. Okay, the internal energy of the system. So how we can represent that mathematically? We are talking about law of equipartition. Here, energy per DOF per molecule is equals to half kBT. Now kB is here Boltzmann constant. And it is equals to R by Na. What is R? R is our favorite universal gas constant, and Na is Avogadro's number. Right? Now there is a doubt regarding what should be the value of R. I also faced it. R is equals to 0.0821. Again, R is equals to 8.336, something like that. Don't need to memorize that. Okay, R is equals to 8.36 or R is equals to 0.0821. When to use which value? Now, actually, they look pretty similar, right? They are just in different units. You take 0.0821 when you are dealing with liters and ATM. Liter for volume, and ATM for pressure. Now, when you are dealing with Newton per meter square for pressure and meter cube for volume, then you take this value. You need to see the units. What is PV equals nRT is the ideal gas equation. Now, what is R? R equals PV by NT. Right? So, when you are dealing with pressure in Newton per meter square, volume in meter cube, then you take this value. But when you are dealing with pressure in liters, ATM, and volume in liters, then you take this value. Okay? Now, let's talk about the law of equipartition. So, energy equals half kBT. This is the sole equation that you need to remember, and other forms will arise from this equation only. If I ask you, what is the energy per molecule, not per DOF, just per molecule, what you will do? I will represent DOF with F, okay, small letter F. You will just multiply with F by 2 kBT. This is for per molecule, just for per molecule. Now, if I say energy for per mole, this is R by Na. You just multiply by Na to make it per mole. If this is for per molecule, multiplying with Na makes it for Na number of molecules, and that's 1 mole. So RT. This was R by Na. This Kb is R by Na. And I multiply it with Na, so only R is left, F by 2 RT. This is for per mole. Now another form, let's say you have N moles. So what is the total energy? nRT. Total energy. This is the total energy. Now, you can get several n number of formulas and equations by altering this equation. You just need to remember that E is equals to half kBT. Now, how this comes about, how is this correct, and how is it derived are parts of quantum mechanics, and therefore not to be dealt in class 11th. Therefore, you will learn these in higher classes if you pursue physics, definitely. Okay? Now, you can try all the alterations and versions and avatars of this equation and get a list of formulas, but you don't need to remember it. Again, I'm re-emphasizing on that. Okay, so with this we come to the end of this lecture. Thank you for watching.